One of the most popular algorithms in near-term quantum computing are the variational quantum algorithms. And in order to run them efficiently, one would like to have ways to optimize cost function using gradients. And in this recent work that we submitted to arXiv, we discuss how to calculate gradients efficiently for this type of algorithms. Now, in general, we usually have circuit parametrization of unitary transformation. And mathematically, this is a product or sequence of exponential functions with some generators of unitaries, right? And the idea here is we would like to find a cost function in the case that we considered that was energy gradient with respect to amplitudes of these unitary transformations, okay? And let's see, as I said already, we mainly were looking at the variational quantum eigensolver, but these techniques that we developed, they can be used for any variational quantum algorithms, not necessarily eigensolver. All right, but in eigensolver, we have energy as a cost function. And in order to calculate this energy gradient respect to amplitude of a particular generator, right? We have this, well, relatively complicated looking expression, but nothing conceptually difficult here really, because this U1 and U2 are really part of the global U. If we want to differentiate a particular generator, because generators, they don't usually commute, or in general don't commute, then we have part of this product that is before the one generator, the one we want to differentiate amplitude for, and the U2 is anything after, right? So then when you differentiate this expression with respect to tau k, you can actually convince yourself that what you're getting is this commutator, expectation value of the commutator, and if one would like to use the same machinery to calculate gradients, then what one would need to do is to construct a wave function, which is U1 acting on the 0 state, then the unitary that we would like to differentiate, and then we would like to calculate the expectation value of this commutator on that function. Which of course is not that easy, because the commutator generally may have well, many more terms than the terms that we had in Hamiltonian, right? Plus that's a commutator of a transformed Hamiltonian, so it becomes sort of a mess, and we would like to avoid that. Ideally, we would like to have a gradient expression that would involve measurement of the Hamiltonian with the circuit which was the same as for the energy. Maybe some parameters are just changed. That would be ideal, right? But the circuit is the same and the measurements are the same. That's the goal. Now it turns out that such goal is attainable, and the work was done back in 2018 on so-called parametric-shift-rule. And the way it works is that in slightly simplified notation, where we, let's say, focus only on the generator that we're interested in, and for a moment forget about other unitaries and the wave function, right? So then this expression can be, as before, differentiated. This difference gives us a gradient, right? And it turns out that this gradient can be obtained for generators that have only two eigenvalues, plus minus some lambda. They can be obtained using so-called shift rule. The name comes from the fact that the gradient is just a scaled difference between the two expectation values of the Hamiltonian, with, again, the same circuit, because the same generator is present, right? And other unitaries, if they are present, they are there as well, right? But the only difference between these two expectation values is that the amplitude for the first one is shifted positively with this S value, and for the second one, it's shifted negatively with the S value, right? So that's what the shift is. And it turns out that this difference is not some sort of numerical approximation to the gradient, but it is exact gradient, surprisingly. But if you look into the algebra, the reason why it's exact, it's similar to the reasoning can be made that if you want to differentiate linear function, then you just need to, like of a normal argument, then you just need 2 points essentially to find the gradient of the linear function. And this works similar way because it turns out, in order to understand how it works, you need to understand that if generator has only 2 eigenvalues, for simplicity, let's say plus minus 1, we'll get to lambda a bit later, right? So if you have G that has plus minus 1 eigenvalues, then you can write exponent as a linear combination of identity operator multiplied by cosine plus I sine multiplied by G. And there are no higher powers of G. Why? Because it turns out for this plus minus 1 eigenspectrum generators, they have this involutory property, and G square is equal to identity. So all powers essentially they will either contribute to G or to identity. And then if you are really looking into the generators that have not plus minus 1 but plus minus lambda, then you need to work a little bit and scale the quantities that you obtain with this lambda parameter, right? And this is how it essentially works, that you can see that one expectation value, you can represent the exponent of the shift as identity plus linear term, and minus shift is the same thing. Then when you do the difference, the zero order terms and the quadratic terms, they just cancel. And what you are left with is exactly the gradient term, where G is on the one side of the Hamiltonian and then on the another side of the Hamiltonian as well. Okay, now how can we go a little bit beyond the generators with just 2 eigenvalues? Recently, there was another work that was considering generators from the unitary coupled cluster single and double, or actually any unitary coupled cluster theory, where you disentangle sort of different fermionic rotations, and the generators essentially that were considered single electron rotations, double electron rotations, and so on. Turns out that all these generators, they have a nice property that they have only 3 eigenvalues, 0, plus, and minus 1. And it turns out that you can do a certain expansion of these generators in, say, to projectors, to plus minus eigen spaces, right? And as well as 0 eigenvalue space. And then the exponent can be represented as a product of 2 projectors, just comes from this representation, because the projectors, they commute, and that's why the exponent can be written like that. Projectors, as you know, they have just 2 eigenvalues, 0 and 1. And if you do maybe a little bit of a shift to move that spectrum to plus minus 1, that can be done, right? So then you can essentially apply the same shift rule we talked about for the plus minus 1 eigenvalue operators, and eventually you can find the derivative of these generators with respect to theta, in this case using just 4 expectation values. There is another way to arrive to the same result. You can simply write exponent as this expression, which involves G and 0 eigenvalue projector. The same sort of conclusion here is that you need 4 expectation values to differentiate with respect to theta. Now, in this work was found that if you're working with real function, it helps because you can reduce further the number of expectation values for obtaining the gradient to 2 expectation values from 4, which is nice. And since in unitary coupled cluster theory we have that property, we can do that. But now the point of our work was asking more kind of general question, whether we can go to any generator with any eigenspectrum, essentially. As you can suspect, eigenspectrum plays a big role in this differentiation process. And the natural question you can ask, of course, is why do we need more? It's like, aren't we satisfied with these two works that already covered two types of generators? Well, it turns out that the hardware vendors, they keep developing various gates. So now there are 2-qubit gates, like say transmon gate and match gates. They can be sort of mixed in various ways. And one potentially would like to differentiate with respect to amplitudes of such generators. Turns out that these generators have 4 eigenvalues, and because they're 2-qubit gates. And the question is how to differentiate with respect to them efficiently. Also, in the problem related to electronic structure theory, unitary couple cluster, for example, method provides the rotations, single, double, and so on, which do not generally conserve electron spin. And ideally, one would like to use maybe a more complicated rotations, which are linear combinations of elementary fermionic rotations that conserve S square or electron spin. And of course, dealing with generators that are more complicated requires more powerful techniques, right? So the bottom line is we would like to do any generator or obtain the gradient for the amplitude of any generator. How do we do this? There are 2 directions we described in our work. One is, as you could imagine, if you have L eigenvalue generator G, it turns out that the exponent of such generator can be written as a polynomial function of degree L-1. So these coefficients, which are functions of amplitude, can be relatively easily obtained. And this is a useful expansion, which we would like to use in the first approach. And the second approach is decomposing generator into low eigenvalue operators, the ones that have only plus minus 1 or maybe up to 3 eigenvalues, and with some real coefficients. Such decompositions, as you can imagine, can be useful if we can find a way to apply, say, shift rule to this elementary operators, ONs, and then combine the results into the gradient of the amplitude for the generator G, right? Okay, let's see how the first approach works, like polynomial expansion. And here, the idea is relatively simple. We look for the gradient of respect to tau as this linear combination where naturally we're just trying to expand on the shift rule idea that we are adding certain shifts, thetas, and we are adding the expectation values with some coefficients Cns. Now, a natural question is how do we find theta n's and Cns? So we find this kind of parameters of our scheme so that this linear combination satisfies the condition that well, we know about this gradient, that it needs to have only linear terms in G from the left side of the Hamiltonian and the right side of the Hamiltonian. Okay. Now, with the L eigenvalues in generator, we can always present the exponent, each exponent actually in this linear combination, as a polynomial of the L-1 degree. And then the idea is that you want to find for a certain thetas, you want to find the coefficients that allow us to get rid of all the nonlinear terms, because if you have G square or G cube on the right or on the left of the Hamiltonian, you want to get rid of it by canceling it from with terms from other expectation values, right? And so by combining all these terms, all we want is just to leave the linear terms. And it turns out because the powers sort of form like they're linear independent, and they can be considered more like a basis. So this problem of finding coefficient is really a linear algebra problem with matrices, and can be solved relatively quickly. Now, the main problem of this method is that the number of coefficients and essentially the number of expectation values one would need to measure on a quantum circuit to get the gradient scales as L squared, right? And that's not a very exciting scaling, because you can see that if you go to the more complicated generators, the number of measurements you would need to do to obtain the gradients and grow quadratically with the number of eigenvalues. Now it turns out that there is a like kind of slight simplification here. If the spectrum of generator is symmetric, it turns out that you get the factor of 2 because of that symmetry, and the actual scaling is closer to L squared divided by 2. These are actual numbers. So for the 2 eigenvalues, we recover shift rule. 2 expectation values are needed. For the 3 eigenvalues, you need already 4, and so on. So, and as we'll see further, that this scheme is not worth doing beyond 2 eigenvalue or 3 eigenvalue operators, right? Because it just scales quadratically with the number of eigenvalues, and that's not very good. Now, the other scheme is a little bit maybe more complicated looking, but the idea is also relatively straightforward. What we do is we are looking for gradient in the also as linear combination, but the shifts are not added to the generator itself. Instead, they are sort of added to the operators ONs, or formed with ONs, and these ONs are elementary operators into which you decompose generator, right? So if you have in mind some low eigenvalue operators, you can try to use them to decompose the generator of interest with some real coefficients. Now, the way it works, if you have, say, these ONs with just plus minus 1 eigenvalues, then what you can do, and how, like, why this will always work, is that you can sort of use the shift rule to the these ON operators, and it turns out that this difference, it's just simply we applied essentially theta n shift here on the expectation value with say minus theta n, and here's plus theta n, right? So we take a difference, and we obtain essentially this expression. And because ONs, if you sum them up, they will sum to the G with some coefficients. All you need is then to find the coefficients that will do the work, essentially sum the ONs into the G. And these are the choices for the coefficients that will guarantee that these terms with such coefficients will sum into the gradient, essentially. Okay, so that's the idea. You could look at the algebra more carefully, and in the paper we discussed the algebra, but this is the basic idea. Now, natural question is how do we do this operator decomposition, and how does it scale with the number of eigenvalues in generator, right? So the good news is that ideally, in the best case scenario, if you have L eigenvalues, you can actually represent such generators with the log L operators, which have, say, plus minus 1 eigenvalue. How does this work? It's like if you have, for example, 2 operators with plus minus 1 eigenvalues, you can add them up with certain coefficients, and you will get the generator that has 4 potentially eigenvalues, right? So you can quickly see that you can make all sorts of combinations with well, binary coefficients here, plus minus 1 corresponding to a spectrum of ON, say. And if you have a case where the coefficients DNs don't lead to sort of some kind of cancellation of the pluses and minus ones, and you really generate your well, new essentially eigenvalues by doing this linear combination, then you can represent really large eigenvalue generators. Unfortunately, not all generators are like that, and you may be not that lucky, and your generator will require, in a conservative case here, the same number of operators as eigenvalues you have. Why this is the worst case scenario, and you cannot get worse than that, because you always can represent the generator as a linear combination of projectors into the eigen subspaces, right, corresponding to the eigenvalues. And you will need only the number of eigenvalues to do that, and each projector has just two eigenvalues. Therefore, you cannot get kind of worse than this, right? So you can already see from this that this approach is kind of more efficient, because at least you will get L as opposed to L squared we saw before. And in the ideal case, it could be log L in terms of operators. All right, here's some illustration of sort of decomposition, and also how the ideal and conservative cases can work. Generally, decomposition of the generator into operators with low number of eigenvalues is a challenging task. Here's why. You can try to do this by first representing the generator as a matrix, right, in some subspace. So if, for simplicity, let's say you have a generator of 2-qubit operator, which is 2-qubit operator, and then you represent it in a space of Hilbert space of 2 qubits. That gives you 4x4 matrices, and then you diagonalize these matrices, and so diagonal part looks like this, right? So now you can do suboptimal decomposition into 2 operators, but each will have, like as you can see here, 0 and plus minus 3, and here 0 plus minus 1 eigenvalues. Or if you really look into this initial matrix, you can actually figure out that, oh, there is an ideal case scenario here, because you can decompose the original generator into 2 matrices that have only 2 eigenvalues, like plus minus 2 and plus minus 1. Or in the conservative case, you can just decompose it into 4 projectors. Now, how do we do this in a more kind of a general case when it may be kind of bigger than the 4x4 matrices? We actually have an approach which is called Cartan sub-algebra decomposition for qubit case. And the way it works is that if your generator generally is like a linear combination of Pauli products, which are just multi-qubit operators, sigmas here are Pauli matrices for individual qubits, right? Then this Cartan sub-algebra decomposition is representing the Hamiltonian, the generator as conjugated with unitary V dagger V expression, which is linear combination of products of Z operators, right? So this V dagger and V, they can be obtained as just a product of exponents of Pauli's, and then large Z's here is just a product of elementary Z operators for individual qubits. The nice thing about these large Z's is that they always have only 2 eigenvalues, plus and minus 1. And then in this decomposition, which can be done if you don't have very complicated generator on a classical computer up front of the calculating the gradients on the quantum computer, right? So the operator ONs, they can be seen as a product of Z's essentially conjugated with unitaries multiplied by coefficients. Now there is some degree, like gauge degree of freedom here, because you can change V somewhat, and that will change the product of z's that you can obtain. But turns out that the number of z products, which will be important for the number of expectation values you need to calculate the gradient, it stays the same. And this can be connected to the fact that when you diagonalize matrix, and this is like operator form of diagonalization, then you usually well, have some degree of freedom on your unitaries, but the number of so essentially eigenvalues will be always the same, and the degeneracy of eigenvalues will be always the same. All right, so now let's see the decomposition results for 2-qubit gates, this transmon gate that we looked at, and it was discussed in the original shift-rule publication by 2018. So it was concluded there that there are 4 eigenvalues, and that's why shift-rule is not applicable. But because we now decompose this transmon gate generator into 2 operators, both they have only plus minus 1 eigenvalues, or actually scaled plus minus 1, because the scaling factors is related to B and C in the original generator, right? So then it turns out you can do the gradient calculation for this transmon gate amplitude using 4 expectation values. And we also did in our work other 2-qubit gates, match gates, and FSIM gates, and everywhere it was like about 4 expectation values, which is a lower number than what was thought before. Now, as conserving fermionic generators, as I was saying, that the usual fermionic rotations, they don't conserve spin, right? So they do not commute with S square. Now, if we make a linear combination of those, we can create so-called singlet spherical tensor operators, T's. And these guys, they conserve spin and can be used to create essentially entangled state corresponding to the right spin symmetry. But they are more complicated, and you can decompose these T operators, which are generators, right? And depending on essentially the way, depending on how likely you, what kind of T operators you're dealing with, there could be more or less auxiliary, this low eigenvalue operators that you need. Now, these are some operators that have single and double excitations that conserve symmetry. And then the number of auxiliary operators we need is right here, so up to 4. And this is this eigenspectrum for the singlet operators, with subscripts corresponding to the multiplicity of eigenvalues. As you can see, the one feature of this eigenvalues or eigenspectrum of these operators is that there's an increasing number of zeros essentially that we're getting, and that essentially tells you that it's better to partition, like take O's where you have lots of zeros, and then maybe plus minus 1, that would be 1 auxiliary operator, and then lots of zeros and plus minus square root of 2, it's the second one, and so on. So you kind of looking at the spectrum, you can realize that, okay, that usually that O's that you need to take, they are going to be containing 3 eigenvalues. So if you try to do the Z products for this case, it's not going to be efficient because Z products, they only have plus minus 1 eigenvalues. And in order to get this many zeros, you need to have a large linear combination of Z's to get some cancellations and essentially obtain this 0 eigenvalues. And that's not efficient. So this is the case where looking at eigenspectrum kind of suggests that it's better to do decomposition into 3 eigenvalue operators, ONs. All right, to summarize, we looked at the general generators with L eigenvalues, and we explore two approaches to formulating gradients for these generators, amplitudes, right? One was the polynomial expansion, where the idea was to present the exponent of generator as a polynomial, but that approach scales as a square of the number of eigenvalues in the generator, and that is not very efficient. Another approach, which was more efficient, is to decompose generator into the operators that have just 2 or 3 eigenvalues. And that approach scales in ideal case logarithmically and conservatively linearly. So you will pay the price of calculating only up to linear number of expectation values for each gradient.